I hope everybody installed the tracker software and no problem anyhow with using tracker. If you watch this video instruction, you will see that almost every step is explained what to do for the first part of the experiment. The instructions are both in English and in Turkish so that everybody can follow it. This is your report template that you are going to use preparing your reports. This is the video that you are going to study on your second lab. Let's open the tracker software in our computer. And drag this movie onto tracker. You see there are two cards, and if you run the video, two cards moving in different fashion. The stopped card moving slowly, but it's increasing its speed, so it's a kind of accelerated motion. The card, which is at the bottom, is going with a constant velocity. They start the motion simultaneously on the first frame, and they go on these rails. Their first position is the same. We can think that this is time t is equal to 0, and while at time t is equal to 0, this bottom card is having a non-zero initial velocity. But if you look at the one at the top, there is this hand of the guy that holding it first, and probably this part is a kind of a propeller. This propeller is just pulling the cart with some forces, creating some acceleration for the cart. So that's why the top cart is starting from almost zero velocity and is increasing its velocity. And at somewhere, it catches the one at the bottom, which was initially in front. So somewhere over here in this frame, the top card is, because of its acceleration, it catches the bottom card. But we are not going to deal with the top card, which on the first part of this lab report. We are going to deal with the top card in the next part. So we are going to analyze the motion of the bottom card first. This is the motion of the bottom card. We are going to analyze this on tracker. The first thing is that we have to set up our coordinate system. Just pressing this corner button in your tracker will show up the axis. The vertical is Y and the horizontal XX. I will drag this origin and I will direct put the origin on that point. Once you finish adjusting your coordinate system, you can make it invisible by just pressing this coordinate system button again. The next thing is that we have to put the scale for position measurements. For this, I'm going to press this scale button and choose New Calibration Stick. The track length is 100 centimeters in this video, so we are going to mark the end points of this track, and we are going to state that the distance between the end points is going to be 1 meter for tracker. Once you have chosen the calibration stick, hold the Shift key on your keyboard and see that your mouse pointer appears to be a square sign, and then bring to the first point and mark it by pressing left mouse button. This is going to be your first mark. And the second mark is going to at this point. Press right over here. As soon as you mark the second point, the tracker will draw this blue line. I will type 1 meter these 2 points and enter. So this way we just select our scale for this specific video. So again, you can make this scale line invisible by pressing this scale button over here. And we are ready to get the position measurements for the card below for each frame. Now we choose this create button and we choose point mass. When you do this, the tracker will form a new small window stating that mass A over there. Let's rename this by cart manual track. This sign is going to be seen on the position measurements on the cart. Before we state tracker how to get in a position measurements and times, let's concentrate on the cart. We have to choose a reference point on the cart so that the tracker will measure its position from that reference point with respect to the origin in our coordinate system. For this, I'm just enlarging this cart by using mouse wheel. I can choose this marked or labeled region on the cart as the reference point to make the position measurements from the cart. In order to do this, I'm just starting with the zeroed frame. The first frame is always the zeroed frame. After selecting the label, you can use the left mouse button while pressing the Shift key on your keyboard to mark the first position data. This is to be done for each frame of the video. Once you select a data point, the computer will bring the next frame automatically. After tracking each frame, the position and time data are simultaneously recorded in the graphing window, X versus T graph, and the data table. There are 14 frames, so all our measurements are done now. But what about the errors in these measurements? There should be error on these measurements because not any device can make measurements without errors. When you look at this enlarged screen, enlarged picture of this card, you can notice that these squares are pixels in your picture. These pixels are the smallest visual information about the picture of the card. For every frame, these pictures are remade for each frame following this motion of the card. And the possible error is going to be once the size of these small squares So it's very logical to take the length or size of these small pixels to be your position error done by the tracker. The next thing is, how can we measure the size of these each squares? To do this, we have another tool again. We come to Create button and come down on Measuring Tools. On the Measuring Tools, select Tape Measure. When you select Tape Measure, you will see this line stating its length from one end to other end appearing. You can direct the ends of this line so that you can bring them to any 2 points that you want to measure the distance. Since every squares, every pixels are very small, what I will do is just that I will, for example, start from 1 pixel from here and I will count, let's say 10 of them and come to 10 and I will just place these endpoints from the starting to the end of these squares and measure it. While measuring it, just look at this number and then record them and divide this by 10. Because I'm just measuring the length of 10 squares and if I divide this by 10, I will be able to just measure the size of one single square. So I'm choosing this one as the starting square. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. And this one is the end square. So I just place the endpoints over here and here. This distance is the size of 10 squares, 10 pixels, and it just reads 1.599 times 10 to the minus 2 meters. So if I divide this by 10, it's going to be 1.599 millimeters. It's the size of one square. And this is going to be my delta x or the error in the position measurements made by tracker. Let me write this over here. This is the error in position measurements made by tracker. You have to write it also in your report. You have to write all the answers that asked you in the report template. You have also changed all of the values and graphics in the template with yours. After determining the error in position measurements, I'm ready to analyze the data produced by the tracker. This is the tabulated form, And this is the visual form. For tabulate the kinematic physical quantities, which are position, velocity, and acceleration, click Table on the Table window and select these parameters. The image of this table should be included in your report. So, what's our model? The position is just a line in time. It is constant velocity motion. So, the model is x0 plus v0 times t. What we do is we try to make this model unique for our case by just determining the parameters in this constant velocity motion in one dimension. We have two parameters, the initial position and its constant velocity. So what we will do is now that we are going to determine these parameters. But how are we going to do this using our data? Let's come to the tracker screen. This is our data. What we will do is that we are going to determine the parameters by analyzing this graph. Come over the graph, just press the right mouse button anywhere on the graph. Just select Analyze. So the new window will arise when you do this. You will see again these data points. What we will do over here, we will make a model breaking by using curve fit. If you select curve fit, the tracker will give these inner windows. You will see this fit. What we mean by curve fitting is that we are trying to determine the analytical function that fits to our data. When you look at this data, it looks like a line. So it remains to be a line. Because the model is already there, I said it's a constant velocity motion, and for a constant velocity motion, the position is line in time. The tracker draws the best line that fits your data. The tracker gives line equation as x is equal to a times t plus b. What these ABs are in our model? This is A and this is B. In tracker, what the tracker sees. They are calculated or fitted by tracker. When you look at these parameters determined by tracker ABs, we just figure out that the initial position looks like 0, but you know the tracker is very delicate in calculating these kind of things. So it calculated to be 2.944 times 10 to the minus 4 meters. So it is 0.2944 millimeters. And constant velocity of the card is 0.7239 meters per second, which is 723.9 millimeters per second. What is root mean square deviation? The root mean square deviation is a kind of measure of distance or difference all data points to the line that the tracker fits as the best curve to your data. The best curve is analytical function. You have sets of data points. Some of them are just on the line, but some of them will be just off the line to a degree. But it seems that all data points looks like that right on time, but it is not in fact. If enlarge this picture, you know some data points are just off the line. How are they going to measure this difference? When you look at certain data at certain time, just look at its position value, whatever this position value, and this position value of your real data is off the curve by how many millimeters, let's say. What the tracker does, it calculates all of these differences and it gets the mean value of it. So the mean value of these differences of each of your position of your data to the best curve fit is this much. And this is in meters. You can read this as 6.067 times 10 to the minus 4 meters. So the root mean square deviation in x is just 0.6067 millimeters. Well, how are we going to use this number to justify the success of our model with these parameter values? The success of our model is determined by just looking at this root mean square value and comparing this to the measurement error which is made on X, the position measurement error value, which is 1.599 millimeters. Since this value, the calculated errors, the average errors is smaller than the measurement errors, we can safely say that this model successfully explains the motion of the cart. Because the root mean square errors for each data, average errors for each data is less than the measurement errors. It is within the measurement errors. That means the best fit line is just within the measurement error made by tracker. So the root mean square always must be less than this measurement error. In that case, you can safely say that your model with these parameters successfully explains or fits to your data. This is how we justify the success of our model by just looking at this root mean square value, whether it is smaller than the measurement value in using same units. If this is smaller than our position measurement errors, then you are done. You have to also insert this graph into your report. Now, we are going to calculate this constant velocity in different way. For this, let me come to the tracker. I will open V versus time graph. When you change this plot window V versus time from X versus time, V versus time data looks as if the velocity changes in time. If you scale the graph to show with 0, you will see that the velocity is almost constant except for very small deviations. V values over here are not data. They are calculated data. They are calculated by using position and time measurements. They are calculated by tracker. These points can be taken as data, but it is not direct measurements. So what we are going to do is that come to analyze, but this time choose statistics. Because this time these data are calculated data. The average of these data, of course, is going to be calculated constant velocity. So the mean value of Vx is going to be calculated constant velocity of the manually tracked card. So this is another way of calculating the velocity. We have already found this constant velocity by using the slope of x versus t graph. Now, the tracker calculated this constant velocity of the card as 0.7239 meters per second by using statistical analysis of calculated velocity data. As you see, they are the same within some range values. And this range value is the constant velocity uncertainty. It is calculated by the tracker as 1.239 millimeters per second. You have to also insert this image into your report. The next thing is that we will define the motion of the same card by using the model making method. For this, let's come to the tracker screen again. Click Create tab and choose Kinematic Model. When you do this, the tracker will form the model A. Let's rename it as Card Model and choose its color blue. To make model, select Model Builder. After this selection, the tracker opens a new window where you will add your parameters and express your model. Add your parameters, which are initial position and constant velocity. And express your model in terms of your parameters. To compare the cards visually, their footprints should be selected as bold vertical line. This selection will allow you to have a visual idea of how well the motion of the cart model and cart manual track match each other. Estimate the constant velocity value for the model, and this will be in terms of meters per second. And by running the frames, check success of this estimated value. We can modify the value to increase the overlap between the model and actual motion. After determining the parameters, tabulate the kinematic physical quantities for the model. This table has to be added in your report. The next thing is comparing the cards data. To compare cards data, just press left mouse button of your mouse anywhere on the graph window and select Compare with. The tracker will open a small window with cart manual track. If it's chosen and the window is closed by pressing OK button, it will be possible to see the data of both cards in a single graph. In this graph, it's seen that their position time data are very close to each other and they overlap very well. So their divergence from each other is very small. This graph should be also added to your report. To show how well their velocities match, let me switch to V versus time graph. On the V versus time graph, we see that all data for the model cards are on a line, which is what we expect to happen because the motion of the model card is defined as a constant velocity motion using the model making method. The velocity data of these cards seems to be very different from each other. But if we again scale the graph to show V is 0, we see that the data points are overlapped very well. This graph has to also be added in your report. What's the next thing? The next thing is that finish the first part of this experiment. This time, we will measure how well the model represents the actual motion of the card using the tape measure tool. If tape measure ends are selected as cart manual track and cart model, the data on this plot is going to be the distance between the measured cart position and cart model position at every frame. If we analyze this data using statistics, value is going to be the distance between the measured position of the card and the position of the model card. In this example, this value is 1.333 millimeters. Since this is less than pixel size, which was 1.599 millimeters, we can briefly say that the model is successful. This image have to also be added into your report, and this will be finished up the first part of the experiment.